In a previous video, I explained in great length what happens when a nerve signal is passed on from one nerve cell to the next nerve cell across the synapse. Right now in this video, I'm going to explain to you how a nerve impulse travels within a nerve cell, along the membrane of a nerve cell. And this nerve impulse, because nerve impulse kind of sounds uncool, we got to give it a better name. We call it action potential. So I'm going to explain now how action potentials are passed on within a nerve cell. And what we have over here, this thick line over here is not really a thick line. This is the membrane of the nerve cell. And this is the outside of the cell, and this is inside the cell, and this is the cell membrane. That's essentially a phospholipid bilayer, whatever. If you know already the structure of a cell membrane, then just think of the phospholipid bilayer. Inside this membrane, we have a whole bunch of proteins, namely sodium channels, potassium channels. K is the chemical symbol for potassium, and we have over here an NAK pump. This is the so-called sodium-potassium pump, and I've given them different colors and different shapes to make it look nice. What I'm going to do now is I'm going to explain you how a nerve signal is passed on, and I'm going to start over here on the left side. And down here are some labels, resting potential, depolarization, and so on. These are the different stages or the different parts of an action potential, of a nerve impulse. And we start off with the so-called resting potential, and the resting potential is the state when the nerve cell is at rest and not firing, and we have a lot of Na plus on the outside and potassium K plus on the inside, and they're separated from each other because they cannot go through directly through the membrane, because the center of the membrane is hydrophobic. They are highly hydrophilic, they're very polar, they do not want to go across. And sodium actually wants to diffuse to the other side but can't, okay? At least not right now, because it doesn't want to go through the membrane because of what I just told you. If you now take a little a voltmeter, and it's got to be a pretty small one actually, and they have done that. They have measured the voltage difference between the outside and the inside of the cell, and they discovered that there is a minus 70 millivolts is on the inside. So the inside is slightly negatively charged. Now that's millivolts. Milli is a thousandth of a volt. It's not a lot, but that's enough. And now we want to pass on a nerve signal. So the cell is waiting here. Okay, it's not firing. There's no action potential going on yet. Because it's waiting to pass on a nerve signal, and it's waiting until it's told to pass on a nerve signal. Then we have a so-called sodium channel protein. There's a little gap, a little hole in the middle, and this is able to open and close. And what do you think is going to happen when it opens? What happens to the sodium, the Na plus on the outside? What will it do? Because we have a high concentration of Na here, it opens up, and then of course it's going to diffuse down into the nerve cell. And in here we still have our K plus from over here, but now we also have our Na plus over here because it's diffusing in, because the sodium channel protein opened up. And this process is called depolarization, and this is the first start of the action potential. And when this happens, then the inside of the cell becomes positive, and it goes up to plus 30 millivolts all the way up, so it becomes positively charged. It's like a charge reversal. And when this happens and becomes positive on the inside, then the K channel proteins, which are located on the in the membrane as well, they say, now it's positive, now I have to open. So the potassium channels open, and what does the potassium do now? The potassium now diffuses out. the K plus diffuses out, and the Na plus is still in here, of course, because it diffused in. But now the K plus is diffusing out, and when this happens, the inside becomes negative again to approximately minus 70 to minus 80 millivolts. So we're back down in the negative range, but now the K plus and the Na plus essentially changed sides. That's essentially what happened. You open first the sodium channels, then the potassium channels, and this allows the diffusion to happen. And so essentially sodium and potassium changed sides. And what happens next is that we have the so-called sodium-potassium pump. After this happened, we gotta bring it back to the original side. We wanted to restore the resting potential again. And this is now the place or the stage when you actually need energy. So what we're doing is we're pumping the potassium back in again. Did I say pumping? Pumping means it requires energy, and at the same time sodium Na plus is pumped out, and this happens at the same time. Okay, so when one is pumped in, the other one is pumped out, but this requires a lot of energy, so ATP is needed. That's important, okay? So it is only this restoring of the resting potential that where we actually need ATP. Everything else over here is a passive process. So here we are charging up the membrane, and then over here, simply by opening it, it's happening on its own. So the last stage is the restoring of the resting potential, and only after this has been completed, the nerve cell is able to fire again. So the action potential, the firing of the nerve cell starts, let's say, over here, from all the way up here, because the resting potential is still waiting, and it stops over here, let's say. Okay, so that is so to say the place where the action potential takes place. Now, how many of these channel proteins are actually there? Well, they're all along the membrane. So what happens is essentially that not only one channel protein and one potassium channel opens up, but all of them subsequently start to open up. So you have a wave of sodiums rushing in. And now I need a little bit more space to draw this. So if this is my membrane over here, what we have is we have the sodium going in subsequently. So it's like a wave traveling. And at the same time, as soon as this is in, the potassium goes out. Shortly afterwards. So essentially, if you want to represent this differently, it's a little bit, it's like going in a spiral. One goes in, the other one goes out. One goes in, the other one goes out. Okay. And after they have changed the places, we need to invest a lot of energy to bring it back to the resting potential. So you have sodium and potassium channels and sodium-potassium pumps all across the membrane over here. So that is basically, what happens over here. But now I'm going to go to the next foil, and you see the same picture over here. And now I'm trying to explain this a little bit in relation to this diagram over here. So there is actually not a lot of new information. Let's just relate what you've just learned to this diagram. So what we have over here, we have the resting potential, it's minus 70 millivolts on the inside here, with the sodium out here and the potassium in here, just like I told you before. The 70 millivolts, we are here. Okay, so that's in case you didn't see it, it's minus 70. Okay, so we're here. So, and then basically the nerve cell is stimulated, but it's not stimulated enough. So if you give, if it's too little stimulation, what's going to happen is the following loop. It's going to drop back to the resting potential. If you give it a little more stimulation, it's going to still drop back. So it must reach this critical value over here. And this critical value over here is indicated with minus 55 millivolts. That's called the threshold. Where do I write this now? Shall I write threshold? The threshold level, and once it passes this threshold level, it's really gonna start depolarizing. That's when the nerve cell starts firing. If you're too weak, nothing's gonna happen. It's gonna go back to the resting potential. So, and now let's assume that we've reached the threshold level, And then the sodium channels open up, moves in, then A plus moves in, and we're now down to plus 30 millivolts. And well, you know what this diagram shows you? Plus 40. Well, yeah, I don't know why. Some diagrams say plus 30, other diagrams say plus 40 millivolts. You know what? It probably depends on the nerve cell. So let's be flexible here. Let's not be too narrow-minded. In any case, the important thing that you should know is that this thing over here is referred to as depolarization. Now, how can I make the link better? I'm just going to say, number 1, resting potential. So I'm going to label this as 1 over here. It's not a 7, it's a 1. I have the German way of writing a 1. And depolarization is all the steep rise over here. So that is that's also number 1. So that's number 2. That's depolarization over here. And I wrote down here it goes up to plus 30 millivolts over here, plus 40. Yeah, whatever. Just make sure when you explain this that you're consistent. And then over here the potassium goes out. And we're back to around minus 80 millivolts, and that's what you see over here. Whoop, it all drops all the way down. Let's say that this is minus 80 down here. So we're all the way up, depolarization and repolarization. We're dropping all the way down. So this is number 3. It's called repolarization. This is when the potassium goes out. And then we have to restore the resting potential again. We got to go back to minus 70, but that's not the main point. I mean, we got to get the potassium back on the right side. So even though the polarization of the membrane does not change a huge deal here, we still got to change the ions around. So that's number 4. And number 4 is the restoring of the resting potential, and that's basically what happens when we pump in the potassium again and the sodium goes out. Okay, and so we're back at normal, and that's restoring the resting potential. That's the energy consuming phase over here. So that's everything else over here that's all passive, but over here this requires energy. And we're back to the resting potential. So the action potential, the firing of the nerve cell, goes from here to over here. And this is the resting potential over here, which is not part of the action potential. And what happens if you try to stimulate the nerve cell before it has finished restoring the resting potential? What's going to happen? Nothing. The nerve cell is simply not going to respond. You have to complete the complete action potential in order for the next nerve cell, to fire again. So what are the milliseconds over here? This is about 1 to 5 milliseconds. So it's 1, 2, 3, 4 milliseconds, one action potential. Yeah, I have seen diagrams where they actually say it takes 10 milliseconds. So which one's correct? Usual answer probably depends on the neuron that you're looking at. But the principle is always the same. So you might now wonder, well, I don't quite understand, because when I have a strong feeling of pain, then shouldn't the action potential be stronger if I feel something very strongly, or if I only feel something very lightly? Should the action potential not be a little bit lower? And I'm saying no. The action potential is an all or nothing process. When it fires to the maximum. So if you feel a strong pain, for example, then you simply have many action potentials. If this is the timeline, you simply have many action potentials. That's a bad drawing. You simply have many action potentials in a short time. Okay, so that's supposed to be one of my peaks. And if you feel only something very lightly, then in the same time you have only relatively few action potentials. Okay, I don't like this drawing. Okay, but I mean you get the idea. It's what you call engineers call this frequency modulation. The size is always the same, but you simply have more action potentials per unit time. So this is a stronger nerve signal than this one down here. Okay, I hope you get the point. So that is basically these two folds now explained to you how nerve impulses are passed on along a membrane. And when it has reached the end of the axon, then you're at the synapse, and then of course you have the whole business with the neurotransmitters, which I explained in a different video. Okay, so that's it.